The radio spectrum is a portion of the electromagnetic spectrum used for communication and data transfers. It is also a frequency of electromagnetic radiation that is emitted by celestial objects, and a critical resource for us to gain a better understanding of the universe. Current systems divide the radio spectrum into designated uses. Split between users, the spectrum has become a finite resource for researchers, scientists, and commercial users. In 1958, to protect sensitive radio astronomy equipment, the Federal Communications Commission established the National Radio Quiet Zone, a 13,000 square mile area covering parts of Virginia, West Virginia, and Maryland, in which radio signals are controlled. The recent development of satellite constellations now poses an additional source of radio frequency interference for radio astronomers, and a new issue faced by the Radio Quiet Zone.
We all have our particular needs, right? So radio astronomy needs clear areas of spectrum that are quiet, and commercial operators need to be able to use portions of the spectrum. The real danger is that you have the telescope pointed in the sky, and you have a satellite that comes and points directly down the barrel of the telescope. You don't want that to happen because you have a sensitive receiver and a powerful transmitter. That's a bad situation.
The primary risk is radio frequency interference. The signals emitted by satellites are far stronger than those of celestial objects, and can easily disrupt scientific data collection.
And so, in order for that not to happen, the systems need to know about each other.
The National Radio Astronomy Observatory, funded by the National Science Foundation, are working with partners on a new way of managing the spectrum's usage, the radio dynamic zone.
The National Radio Quiet Zone was an area where the emissions of transmitters would be very limited, and a dynamic zone is a region where the transmitters and receivers would be in communication with one another.
The largest satellite constellation by far is Starlink. With thousands of satellites in orbit, they provide an internet connection for over 70 countries.
One experiment we're doing is a pilot program with SpaceX. SpaceX operates a system called Starlink, which is a spaceborne low Earth orbit system that allows people in remote locations to connect directly to the internet. With very low latency, there's not much delay, and with also very high throughput, so you can do data transfer. We have been working hand in hand, performing experiments both out at the Very Large Array in New Mexico and also at the Green Bank Telescope in Green Bank, West Virginia. And from the fall of 2021 until right now, we have been carrying out experiments in coordination with them to try to figure out these protocols, how this might work.
The technology inside a Starlink satellite allows these systems to work together to avoid this radio frequency interference.
So what's particularly flexible and powerful and configurable about the SpaceX Starlink network is that both their downlink and uplink antennas are what are called phased arrays. And so they're actually steered electronically. So it's not what you might think of as a traditional parabolic dish that moves around. It's actually just a flat panel, but the circuitry inside allow that to steer either a transmitting beam or a receiving beam in any direction. So because it contains that sort of an antenna, their system can actually steer that beam actively far away from where our sensitive receiver is. The other thing that's really helpful about their system is that it updates very quickly. If you think about how quickly a low Earth orbit satellite moves, we're looking at a small patch in the sky. Their satellites are typically moving through our area of concern in a matter of seconds. So if their satellites can do something different for those seconds, that solves our problem, and it doesn't affect their system negatively in a huge way.
Communication between these two systems is essential if we want to continue to be able to use radio astronomy as a research tool.
We're building a software system called Operational Data Sharing. And what ODS will do is it will populate a data site so that the satellite network knows where we're pointing in the sky, what frequency we're operating at, and how long we'll be there. And so knowing those things, their satellite network can actually adapt to what we're doing. The plan is to build a system that works with our radio telescope and their network, and then to try to generalize that into a system that could potentially work for any radio telescope and any satellite network. So I'm excited about it because I think this is what we need to do to make radio astronomy viable for the coming decades.
For more news on science and technology, subscribe to One World Network.